Okay. Okay, so far so good. What if we need to add the last element? It's not as simple as adding the first element, because in the first element, the first dummy element, we have a leading bookmark, which is head, whose value is the pointer to the next element. So we may access to the first, we may access the first, the leading bookmark, and it will provide the pointer to the next element. So, and this is what we do here. We access the element pointed by head and copy to element, and then we update it. But if we want to add the last element, we cannot access the content of tail, because tail points to none. So we must access the node pointing to tail. It's okay for everyone? And we do not know in advance which is the node pointing to tail. We must traverse the list in order to see which is the node whose value we know that is this one, whose value is tail. And how many iterations do we need? Of course, the answer is of course, the answer is that it depends on the length of the list, of the linked list. Okay. We may also this function adopting a recursive approach, but I prefer to use an iterative approach. If someone wants to implement in a recursive approach by his own, is most welcome. Okay, let's give a look at this function. Add last requires, of course, the list and the element. We have a variable which is current, which is initially set to head. So we start from the head. We start from the head. And while current is different from tail, okay, look, we define a new node, which is, for example, next, which contains the value of the current node, namely the pointer of the current node. And if next is equal to tail, if we arrived to the next to last element, now we may, this is the correct point to insert the new node. And the idea is precisely the same. We create a new key, which is E, the element, whose value will be L list of car. So the old next to last element. And we update the next to last to be to point to the new element. And of course, we break the while loop because there is no need to iterate, to perform more iterations. We finally, oh, this is wrong. No, if not, we update the current node, which is equal to the next. So we move one step forward and continue iterations until it happens that car is not different from tail, so it coincides with tail. Is it clear what we are doing? So we of course, this function relies on the existence of pointers contained as values of the pairs key node of our dictionary. So we start from head, and while, which is the current, and while current is different from tail, we access the node for the pointer to the next element, which we call next. And if this condition is false, suppose for a moment that this conditional is may be absent from this code. Sorry, excuse me for a moment. So suppose for a moment that we do not have this conditional. What we have is that next is the value of the current node. Then we update the current node to contain the next, and this allows to proceed in let me show for a moment which answers the question how to print in order all the elements of the list. Let's call print all as a list. We start from we need to know which is the starting point. And by convention, the starting point is the head, so the leading bookmark of our list. So while car is different from tail, in this case, what do? We simply print what? We print car, which is the key, and a list of car, which is the value. Okay? And equals and now car, the new is list of car. Okay, so we update the current node to be the next one. Oh. Okay. No.
Because A is pointing to the end.
Yes, but we stop earlier. Unless we do this. Okay. We stop earlier. We never will when car is tail. We do not examine we perform the iteration unless no there is no, there is a way. In this case, we could do something like
I don't know why it's pointing here.
this way.
Add to B, B to I, A to tail. I've done it. No, I
yes,
copy your
why
photo.
not? Yes. But okay, add refers to B, B refers to A refers to tail, tail refers to now. May also, for example, add first as least C. What's happening? There is something wrong if C points to C. Okay. Okay. Okay, now it works. The point is that in our function add first there is no that may prevent the occurrence of more keys with the same value, of more nodes with the same key, which is wrong. Okay, so in that case, it happened that head points to C, which was the first insertion, and C point to B, and that was good. Then I inserted again C, and so what happened was that head pointed to C, and C pointed to C itself, which was the old C. Okay? So it never goes out of a kind of loop, because C points to C and never proceeds. So we should, if element in a list return -1, let's say, or if element not in list, which is much better, okay. So if element is not in list, so if the node is not already in our list, it will be created. Okay. Okay, now it works because it did nothing. We may remove this one, we may remove this one, we may remove this one as well. Is clear for everyone?
Yes, Professor.
Okay. We have seen how to traverse a singly linked list. Please note that we cannot traverse a singly linked list the reverse way, starting from tail and going backward, because we do not have any pointer to the previous element. This lack will be overcome in the doubly linked list, in which we have two pointers, one to the previous element and one to the next element. So we may traverse our list in both ways, but it's not. Now we want to implement our add last function.
Can you go back to the code where you implemented it not in the list?
So let's figure out how to implement this add last. we need the okay, let's define an element which is next, which is a list of car. Okay, and we also need the car at the end. The car must be updated to point to the next element, which is precisely this instruction. Okay. If current is the node pointing to tail, so if current is the next to last node in our list, then this is the current point in which inserting our new node. It's okay. So if next equals to tail, what do we have to do? We have to insert element. Only if the pointer of the current node is tail. So only if, so the idea is that, of course, we begin from the head. The value is B. We update, so current becomes B. B is a value equal to A, so the next element will be A. Current will be now A. It's the next iteration. The new, the pointer of A will be is a tail, precisely where the insertion must be carried out. Okay? Is it clear? All of you? Yes, no, maybe? Okay. Any question? Any question at home?
Just one question, Professor.
Yes.
Here in the atlas function, we have the same problem as in the function, that if an element is repeated, it will.
Yes, you're right. You're right. I forgot to break, first of all, in order avoiding to continue the traversal of the list. This is the first. If next equals to tail and element not in a list. Thank you very much for your contribution. Okay, so instead of coding a nested conditional, so if next is equal to tail and if element not in list, as both conditions must be true at the same time, okay? Okay. So this is our function. And finally, or we could even return a list with a new So look, it worked. This was the old configuration: add C, CB, BA, A tail, and now AD, D tail, tail none. Okay? If we add one more time D, yes, will never be true. Will never be true. Okay? Clear for everyone? It's okay at home too?
Yes, Professor.
Yes, yes, there's a, yes, yes. This is wrong. Okay, it's okay for everyone. And now an element from a singly linked list. Remember that linked lists are the data structures commonly used for phone books, for example. Therefore, we may need to insert new contacts and remove contacts. So it may happen that we need to do it. Okay, let's first discuss how to remove an element from the head of a list, which is precisely the reverse of the insertion. In the reverse of the insertion, how to do? Del first is the function that implements the removal of the first non-dummy element from the list. Okay? The first non-dummy element of the list is the one pointed by head. Okay? Therefore, we must act on the head. We must act on the head key of our list. So the idea is that we first preserve the store of the movement of the we first the value of head, so the pointer, the node pointed by head, and we call it x. Now we must update the pointer of head, which shouldn't be anymore x. Rather, it should be the node pointed by x, because we must now skip head and update the pointer of head so to point to the pointer of x. When we have carried out this update, we may finally remove the pair x and its pointer.
If we use the second instruction, we will lose the pointer.
Yes.
We lose the value with head.
Yes.
Now with the pair.
Yes. Okay, so first get let's call x the node you want to remove, which is pointed by head. Step 1. Step 2, update the pointer of head, which must contain the pointer of x. Okay? And finally, destroy the old element. So the idea is that in this situation, we have that head which is the first pair, and C, B. Oops. It's okay for everyone. And it must become head It's clear for everyone? Yes, no, maybe. It's clear for everyone at home too?
Yes, Professor. It's clear.
Yes, Professor, it's clear.
Okay. So, with this in mind, we go up we have no choice. The element to be removed is the one pointed by head. So there is no choice, okay? And now we have to update the pointer of head, which will be x no more. It will be the node pointed by x. So we must write a list of head equals a list of x. Okay, so the node pointed by, and now we may remove. Yes, yes. It's okay. Okay, we destroyed C, and we updated the pointers so that add points to B, and all the remaining part has been okay. It's okay for everyone.
Yes.
Yes, Professor, it's clear.
Are you going away? Are you going away? Oh, good. Yes, before going on, I would like to begin a review. Okay, so the review is the following: implement the function remove with arguments list and e, which traverses so you cannot remove the element. You are not supposed to destroy an element from a dictionary. This is not the goal. Instead, you have to traverse this list, and if you find the element, the node E, you destroy it, of course, while preserving the integrity of the singly linked list you are traversing. It's okay? Is it clear? Okay, come on. Is it clear at home too?
Yes.
Yes, it is clear.
Yes.
you go back to the code for delete the list?
May I? Sorry?
Go back to the code for the deletion of the list.
Which one?
For the deletion. How for to delete the list.
Okay.
Delete the list.
This one?
Yes.
Okay. Any result?
I think it doesn't mean like I look to the end and I implement a combination of tags. It will be
Okay.
analyzed and it will be not in list.
E must be in list. So this second part is irrelevant. This is why it does not work. Have you done? Does it work?
Yes. This was the previous one. And then I remove the 3.
He at least while
I'm sure that like else
okay,
with
while
error.
at least is different from E. No, because if you replace this one with, let's say, 9, how to run again?
It's not doing that. I mean, I should have like an error message, like the element that you want to delete is not in the list.
If
Just this value should be like
just a moment,
1.
please.
Sorry.
Why? Oh, okay. Okay. So you first you search for the occurrence of. Okay, and so okay. Yes.
What I was thinking is like I can traverse all the list until I get my element. If once I find my element, I can delete,
But
create new links, and then delete it. The only thing is missing is like maybe I don't know.
how to get out of this while loop if you don't find the element.
If I don't find it, I'll not go inside the loop because I.
Okay.
So what I have to add is an else condition. Let's say error.
Okay. Well done.
But I'm sure that it can be done maybe in a shorter way, or not.
Yes, but it works.
Professor, I sent my solution that it's not working, but I can't. I don't know how to make it work.
First of all, your condition that element must be different from tail is nonsense. This is the first.
Okay.
This is the first element. And also the update of pointers is wrong, Radishi. You should fix this one. You are not interested in updating the value of element pair. Instead, you want to update the pointer of current.
Okay.
Sorry?
Not able to plug the else inside the function. Send to me syntax error.
Yes, because return is at the same level of if. So it's it's not it's.
It's like breaking the line.
Yes. You are supposing to closing the if. Okay. We have a list containing elements: head pointing to F, pointing to C, pointing to B, to A, to D, to G, to tail, to none. This is the initial situation. We want to remove as list, let's say A. What's happening? What's happening? Oh. Okay, it works. So this is the remove function, a possible implementation. Some of you have devised which are as good as mine. I mean, so the first idea is to check if the element is contained in the list. If not, nothing happens. We begin from the head of the list, which we initially call car, and while current is different from tail, we create a new variable next, which contains the node pointed by current. So we have currently two variables, the current node, which is car, and the next node, which is next. Okay, if it occurs that next is the desired element, we simply have, if next is equal to E, what we have to do is to update the pointer of current in order to skip the element. So the pointer of current will be the pointer of next. So we skip the element we want to delete. We delete the element and return the new list. If this is not the case, we simply update the current in order to proceed in our traversal of the list. Okay? It's okay?
After the code that I show you.
Sorry?
After the code that I show you.
Yes?
If I remove an element, try to remove an element, which is not inside the list, I don't know why all the lists get cancelled.
All the list?
Get cancelled. I don't know why. If I remove an element that I don't have, and I try to print the list, the result is none. It's
a little bit puzzling. Okay. So how may we remove the last element from a list? Yes.
Same thing that we've done now.
Sorry?
Same thing that we've done now.
Yes, but the idea is that we still have to maintain two information about two nodes, current and next. If it happens that next is the if it happens that L list of next is, so we have to stay one step back. Be careful. If we have to remove the last element, the last real element, which is in this case, in this example is G, we must analyze not next, rather list of next. Okay? Because we have to work on the pointers, on the pointer of D, not on the pointer of G. It's okay? Okay, so we have to analyze the pointer of the next. And of course, the problem arises from the fact that we cannot traverse the list backward from the tail to the head, because we have no links which allow us to go backward. Instead, we may only traverse our list from the head, from head to tail. Okay, so let's implement okay, the first the last of a list. Okay, let's give a look, please. As before, we begin on the head, and we have slightly little change in that we don't need to stop when car is tail. We may stop one step earlier. Okay, so when a list of car is different from tail. So next is a list of car. So is our next node. If the node next to the next is tail, if the next to the next is tail, remember, what we have to do is what follows. We have head, N1, N2, let's say N7, N8, tail. Goal is to obtain something like this. It's okay? So we must act on N7 because we must skip N8. So we are not interested. The condition in which we must act for our removal is not when next is tail, but when the next of the next is tail. Because we must modify the pointer of the current node, which is when our node, when current is N7. Okay? So when current is N7, we must take the next of N8, which is tail, and we must remove N8. It's okay? It's okay? So this is our, and the last. Okay, so G has been removed. Is it clear for everyone? Okay, so the review for is implement the function swap list E1 E2 that implements the swap of the nodes E1 and E2 of a singly linked list. The integrity of the list must be preserved. Deadline tonight. Code in my personal chat on Teams. So you first have to check that E1 and E2 are adjacent, okay, are contiguous. This is step number one, because okay, it's not necessary, actually, it's not necessary. So no, forget. There is no need to check for adjacency, for contiguity. You simply have to switch these two, to swap these two nodes. Of course, the important element is that they both are elements of the list, are nodes of the list, in which case you have to preserve the integrity, namely the element which stands before E1, let's suppose E1 comes first and E2 comes later. Okay, so the node pointing to E1 now must point to E2, and the node pointing to E2 now must point to E1. Okay, so the idea is that you have to determine which you need 2 pointers for each node, for each of the 2 nodes. The node pointing to E1 and the node pointed by E1, and the node pointed by E2, which points, and the node pointing to E2. So suppose the situation is this one. You have, let's say, 3 pointing to E1, which points to 6. And then you have 10 pointing to E2, pointing to, okay, suppose this is your situation. What you need is to update the pointer of 3 and the pointer of E1, and the pointer of 10 and the pointer of E2. Okay? So you traverse the list. When next is E1, you store the first pointer. When next is E2, you store the second node. These 2 nodes now must be updated, because the first one, which contains E1, must contain E2, and vice versa.
So the pointer of 3 will be assigned to the pointer of 10. So the pointer of 10 will be assigned to the pointer of 3.
Yes. Okay. Is it clear for everyone?
Yes, Professor.
Yes.
Professor.
If there are no questions, we may stop here. And see you tomorrow morning.
Okay, see you.
You're welcome.
Bye, Professor.
Bye.